510 is just, what is optimization, and then 5.11 is let's do optimization. So we're just going to do that together. So what is optimization? One of the most common applications of calculus involves the determination of minimum or maximum values. Consider how frequently you hear or read terms such as greatest profit, least cost, least time, greatest voltage, optimum size, least size, greatest strength, and greatest distance. Before outlining a general problem-solving strategy for such problems, let's look at an example. So in example 1, a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimension should the box be in order to produce a box with the maximum volume? So what I'd like you to do is use your highlighter, and we see something about surface area and volume. Okay, we see something about surface area and volume. So what's going to happen typically is we're going to need to use two equations. We're going to call them the primary equation and the secondary equation. The primary equation is the one connected to what you're trying to optimize. Let me repeat that. The primary equation is usually what you want to optimize or maximize or minimize, okay? So I'm going to write it like this. So my primary equation, I'm trying to find a maximum volume. Well, the volume of this open box would be, based on how I drew it, x squared, that's the area of the base, times the height. That's my primary equation. My secondary equation, they're telling me information about the surface area. Well, my surface area would be, I have the bottom of the box, and remember, it is a square base. Even though it looks rectangular, it's supposed to be a square base. So then I have four sides that would have an area of x squared plus 4xh. And that's my surface area. So I have a primary equation and a secondary equation. So now we're going to make a beautiful connection here to everything we've been doing. Yeah. Can somebody answer that? Why is it not 2x squared? Yeah, Logan?
This is the manufacturer wants to design an open box, which means that the top, there won't be a top.
There isn't a top, but that's an outstanding question. Okay, if I had the whole box, then absolutely it would be 2x squared. Okay, good thinking there. All right, so now, again, we're going to make this beautiful connection. Okay, so when we've been doing relative maximums, it's giving me goosebumps. This is exciting, okay? This is the punchline. Here it comes, here it comes. So we've been working with relative maximums and relative minimums. So guess what? We have to do either the first derivative test or the second derivative test to find those maximums or those minimums, okay? So cool. So here's the deal. Right now, I have two letters, and I don't have any numbers about one or the other. So watch what I'm going to do. I'm going to play the what do I know game, and I know the surface area. And I also know that if I could solve this for h, I can go plug that in and find the derivative. Now, this is different from related rates. Okay, related rates are that you have two variables with respect to a third time. I don't have this is not a related rate. Okay, so now I'm going to go to my primary equation because that's what I want to maximize. And so I'm going to want to find a derivative. And so I typically want to get this down to one variable unless I have more information. So one of those x's is going to cancel, and so I'll get 108. You know what, I'm going to leave that factored. I think that might help me. No, maybe not. Okay, let's see. Factor, not factor. Let me look. How about this? Let's do 108x minus x cubed over 4. So 108 divided by 4. Anybody know what that is? 108 divided by 4. 27. So that's going to give me 27x minus 1/4 x cubed. So what I want you to notice is that we used the secondary equation to substitute into my primary equation to give me one variable. Does that make sense, what I've done? All right, now I'm going to find the derivative. And you can either do the first derivative test, where you see where it changes, this would be from increasing to decreasing, or you can do the second derivative test. On this one, I'm going to go ahead and do the second derivative test because it's kind of easy to do. So if I do the second derivative, if I bring down that 2, that would be 3/2 x. But whoops, I forgot to get my critical points, didn't I? So let me go grab those. Thank you. Yep, I think it didn't catch it when I wrote it, but thank you. So let me go grab those critical numbers. So x is plus or minus 6. Now I cannot have a negative measurement on a box. So my critical point or my critical number would be x equals 6. So then watch this. I go plug in to the second derivative. And I don't really care what the number is, but I know it's negative, right? So x equals 6 is the location of a relative maximum. So then let's go back up here and we can go find h, right? Can't we find h? If we know x is 6, so let me give you a head start on me and go figure out what, or no, not there. Yeah, you could do that there. That's fine. That works. So go figure out h. So what's h? Anybody got it? 3. So if you're still working, keep going. Then what we're going to do is we're going to reread the problem. So I'm getting h is 3, and the problem said, what dimensions should the box be in order to produce a box with maximum volume? So this would be x by h. So we're going to say 6 inches by 6 inches by 3 inches. And there's all your supporting work. Note, there are many possible types of boxes with varying dimensions that yield different volumes. But there's only one that will maximize it, which is the one that we got right here, this 6 by 6 by 3. This is really cool. Super cool. All right, so here are guidelines for solving applied minimum and maximum problems. Number 1, identify all given quantities and quantities to be determined. If helpful, make a sketch. You're not always going to be given the sketch. Write a primary equation for the quantity to be maximized or minimized. Reduce the primary equation to having one independent variable, and this may require the use of a secondary equation. Not always, but overwhelmingly, yes. Number 4, sometimes you have to consider a feasible domain. Like when I did my critical point, it made no sense to have -6 as a possible x value. Determine the desired maximum or minimum value by using the techniques that we used, like the first derivative test or the second derivative test. All right, so let's look at example 2. And again, my hope was to get through example 3 today. I think I'll be fine with that. Example 2 says, which points on the graph of y equals 4 minus x squared are closest to the point of 0, 2? All right, well, we need a sketch here. 4 minus x squared. This is a parabola that opens down. So if I plug in x is 0, I would get 4. And if I let y be 0 and I want to find the x-intercepts, what would be the x-intercepts? 2 and -2. And now I have enough information. So this is my parabola that's opening down. And what I'm trying to find is which points are closest actually that would be just -x, y. So I'm trying to figure out which points on the graph of the parabola are closest to 0, 2. So the question I have for you is, what am I trying to, and I'm actually trying to minimize, right? I'm trying to minimize here. I'm trying to minimize what? Distance. Oh, so my primary equation is going to develop from the distance formula. You see that? Like, that's really neat. That's super cool. So my distance would be the square root of x minus 0 squared plus y minus 2 squared. That's my primary equation. My secondary equation is going to be the y equals 4 minus x squared. Now, I want to mention something that because if I try to do a derivative of that square root, like that's going to be nasty. So what I can do is I can actually square both sides. And then let's multitask. Let's substitute. I'm going to square both sides, and I'm going to replace y with 4 minus x squared. And what I'm going to tell you, you are allowed to do this, is that if I go ahead and find the derivative of d squared, okay, with respect to d, then that's really going to do the same thing as if I just did it with d. It's just a little less messy, okay? Just kind of stay with me here, and this will make a little more sense. So I'm going to do d squared equals x squared plus 2 minus x squared squared. And now I'm going to do the derivative. So I'm going to bring down the power, decrease the power by 1, and then d prime, because that's the chain rule, okay? I had d squared. It wasn't just d. So then I get 2x plus 2 times 2 minus x squared to the first, chain rule it, and again, you could have left it D, it just was nastier, so just, this I thought was a little bit easier to do. Let's go ahead and let's divide everything by 2. So that's going to cancel this 2 and this 2, but I'll have a minus 2. X times the 2 minus x squared. I'm going to do this a little bit slower. Some rough algebra here. So that's x minus 4x plus 2x cubed. So this is d times d prime equals 2x cubed minus 3x. And then watch this. Now I'm going to divide by d, but what is d? D is the square root of x squared plus, and I'm going to use my substitution, that was 2 minus x squared squared. All right, that's like a lot. It's very, very advanced, okay? So I know that that's a little confusing here. All right, so do you see that here's my d, right? This is my d, and when I plugged in that y was 4 minus x squared, that did tidy up to that, okay? So this really is d. So I just divided both sides by d. All right, so this one might require a little bit of like looking back at it, and we're really thinking about it because we're very, very high level right now. Okay. Say that again. It's the distance formula, the d. So this is d, right?
Yeah.
Okay, and what I did is x minus 0 is just x, that's squared. Then this was y was 4 minus x squared minus 2 squared. Yeah, that's where I kind of skipped that part. Okay, so now I need to find the critical points. And that'll be where the numerator is 0. So that's going to be 0 or 3/2. Whoops, sorry, that's not true. Sorry. I was like, wait, I'm not getting my right answer. Let me come back up here. I factored that in correctly, right? And when you factor out the x, you should get 2x squared minus 3. So x is 0, or you set 2x squared minus 3 equals 0. Well, d prime cannot have x be 0. Because that denominator is never 0, okay? The denominator is never 0. So then this is going to happen at x is plus or minus the square root of 3/2. So then you would have to plug that back in. Oops, I lost my 4. 4 minus that. So that's 5/2. So at what points is y equals 4 minus x squared closest to 0, 2? This is really, really cool. It's plus or minus the square root of 3/2, comma, 5/2. And I did the first derivative test on this one. You know what, minus, plus, minus. So oh, whoops, and there was a 0 in there. There we go. That's why it was at negative square root 3/2 and positive square root 3/2. That one was a tough one. Yeah, Daly? Oh, I did. I'm sorry. I did. I put it on there. I did put it on my number line test. Now, the square root never happens to equal 0. That denominator here, this one right here, I'm sorry, I misspoke. I do use x as 0. I just meant that that denominator is never undefined. It's never undefined. Sorry about that. Yeah, it's a, yeah. D prime, I'm looking at critical points where the first derivative is 0 or undefined. So it is 0 at x is 0 and x is plus or minus the square root of 3/2. But it's never undefined because that square root was never 0. I'm sorry, I misspoke. All right, let's go ahead and get started on example 3. A rectangular page is to contain 24 square inches of print. The margins at the top and bottom of the page are to be 1.5 inches, and the margins on the left and right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? So, my primary equation would be the area of the paper is, I'm going to call this y plus 2 times x plus 3. Because along the one side, you're adding 1 inch to each margin, so that's a plus 2. And on the other one, you're adding 1.5 inches on each margin, which is plus 3. My secondary equation is that I know that the rectangular page of print is 24 square inches. So that's x times y equals 24. So what I chose to do is I chose to solve for y in my secondary equation. And get it in terms of a. All right, so I'm going to FOIL this. So that'll be 24 plus 72 over x plus 2x plus 6. So that is super ugly. And again, some of this you're going to really want to go back through and think. I'm not giving you as much thinking time as I would typically like. But, you know, 24 over x times x. Do you see how the x's cancel? You know what I mean? So you just might need to think about this a little bit. All right, so now I'm ready to take the derivative. 72 over x is really 72x to the negative 1. So that's negative 72 over x squared plus 2. I'm going to set that equal to 0. Oh, you know what? Note that x has to be greater than 0, right? Because you can't have negative dimensions of a piece of paper. All right, so you can either do the first derivative test or the second derivative test. I'm going to pause and let you try and figure this out. I went ahead and did the second derivative test because that second derivative was pretty easy to do. And remember, you don't always have to like get the number, but it's positive. So at x equals 6, we have a relative minimum. So if x is 6, then you come back up here, and what's y then? 4. Okay, so now, that's actually not my answer. Let's reread the problem. It says, what should the dimensions of the page be? So remember, you've got margins, right? You've got margins on the page. So my answer needs to be, what should the dimensions of the page be so that the least amount of paper is used? It's not 6 by 4. What, in fact, should it be? Good job. Yeah, okay. Those would be the dimensions of the paper. 9 inches by 6 inches. Alrighty, I'm going to stop there. And we will finish this on Monday. But what I would strongly recommend that you do, these problems take a while, okay? So I recommend you do at least 3 problems on the 5, 10, 11 worksheet.